Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on November 28, 2025, about 4 days ago. It introduces a new attention mechanism called hierarchical sparse attention that lets a 1 billion parameter equivalent model handle ultra-long contexts and still score over 90% accuracy on many in-context retrieval tasks, with sequences stretching to 16 million tokens, even though it was only trained on windows up to 32,000. The paper is titled, Every Token Counts, Generalizing 16M-Ultralong Context in Large Language Models. And as we will see later, the approach could really reshape how models remember and search through their entire history. Alright, Figure 1 shows how the model handles the classic needle-in-a-haystack retrieval test across massive context lengths. The heat map stays fully green, which means near-perfect accuracy, from 4,000 tokens all the way to 16 million. The vertical red dashed line at 32,000 tokens marks the trained range, so everything to the right tests pure length generalization. Depth percent on the left indicates how deep in the context the needle is hidden, and performance remains flat and strong across all depths. So, while Figure 1 highlighted how well the new method scales, Table 1 probes a prior sparse attention method called NSA, and how it behaves with and without rope positional encoding. The table reports accuracy on single needle in a haystack and multi-query needle in a haystack at growing context lengths. NSA, without rope, consistently scores higher, especially as sequences move beyond the 4,000 token in domain range. The gap widens at 32,000 and 64,000 tokens, which signals that rope hurts length generalization for this architecture. Well, Figure 2 compares how hierarchical sparse attention and mixture of experts process a single current token, so that the analogy becomes very clear. On the left, the current token first scores all past chunks via their landmark summaries. Then, a learnable retrieval module picks the top K relevant chunks. The token attends to each chosen chunk separately, producing several candidate outputs. On the right, mixture of experts performs the same pattern with experts instead of chunks. Finally, both sides fuse those multiple outputs using a weighted sum based on the learned scores, which means the model can learn where to look rather than scanning everything. Alright, Figure 3 lays out the full HSA-UltraLong model architecture, which stacks a local decoder and a global decoder, so the system can mix short-range and ultra-long-range information. The lower decoder uses sliding window attention, plus mixture of experts blocks on raw tokens. A middle layer produces chunked hidden states, adds special class tokens, and feeds them through a bidirectional chunk encoder. The upper decoder then applies sliding window attention together with hierarchical sparse attention over these chunk summaries, repeating this group several times so global retrieval can refine the representation at multiple depths. So while Figure 3 unpacked how the system is built, Table 3 shows how that design stacks up against strong baselines on real benchmarks. The table compares QN 2.5, QN 3, a transformer mixture of expert space model, and the HSA-UltraLong variants across general, math, and coding tasks. Despite using far fewer training tokens, the dense HSA-UltraLong base lands only a few points behind QN 2.5. The mixture of experts' HSA-UltraLong models match or slightly exceed the transformer mixture of experts' baseline, which suggests that the new hierarchical sparse attention layers do not sacrifice standard task performance while enabling ultra-long context. Okay, Figure 4 shows how length generalization actually behaves on needle-in-a-haystack style tests. The top heat maps compare single needle accuracy before versus after long context mid-training, and accuracy goes from collapsing beyond about 1 million tokens to staying uniformly high even at 16 million. The bottom plots track harder multi-query and variable tracking tasks, where models with shorter sliding window attention during training keep strong performance much farther out in sequence length. Together, these panels argue that both the training data's effective context and the sliding window size strongly control extrapolation. So while Figure 4 focused on accuracy at huge context lengths, Figure 5 turns to raw speed. The left training panel shows flash attention 3 slightly faster at 4 to 16,000 tokens, but by 32,000 tokens, the hierarchical sparse attention kernel becomes meaningfully quicker. The right inference panel makes the advantage clearer, since flash attention 3 times blows up past 32,000 tokens, while hierarchical sparse attention stays almost flat even to 256,000 tokens. So to wrap up, the big message is that hierarchical sparse attention lets models remember and search through contexts millions of tokens long, while staying competitive on normal benchmarks. The work also hints that training on genuinely long documents is crucial if we want agents with real, persistent memory. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.